Hello, everyone. This is Riccardo Calaon, and in this video, I'm presenting my paper titled Attitude Reference Generation for Spacecraft with Rotating Solar Arrays and Pointing Constraints. And I would like to start this presentation by talking about some of the more recent space missions that have been performed in the past 2 decades. First one being the NASA Deep Space One, launched in '98, which targeted the asteroid Brile. The Hayabusa missions 1 and 2, which targeted asteroids Itokawa and Ryugu. ESA Smart 1 launched in 2003, whose destination was the moon. And again, the NASA Dawn mission launched in 2007, which targeted the asteroids Vesta and Ceres. The Bepi-Colombo mission launched in 2018, which targeted Mercury. And finally, the more recent NASA Psyche mission launched at the end of 2023, whose final destination is the Psyche asteroid. Now, the reason why I'm showing these missions and the design for the spacecrafts is because I would like to point out some similar traits that all these spacecraft have in their design, and also point out the fact that the limit for the spacecraft in terms of where they can reach in outer space is the inner solar system. Specifically, the spacecraft that got the farthest reached the asteroid belt. Why is this the case? This is the case because electric propulsion has become the go-to design for most missions in the inner solar system, thanks to its better delta V to mass ratio. Also, all of these spacecraft except the Hayabusa 1 and 2 feature rotating solar arrays. This enables the arrays to rotate about a certain body fixed axis to track sunlight and therefore maximize power generation. In some of the more recent mission designs, the electric propulsion thruster has been mounted on a dual gimbal that in principle allows to track the location of the center of mass over the course of the mission as mass is being depleted. Now, this all sounds great in terms of new capabilities that can be provided to the spacecraft. However, these new capabilities come with modern problems. Specifically, attitude remains a three-dimensional problem, and therefore we have a bunch of constraints that we need our spacecraft to meet in order to operate nominally. The first one, for example, just aligning the thruster with the inertial request that generally comes from trajectory optimization is a two-dimensional problem. So it locks 2 degrees of freedom for the spacecraft attitude. Now, rigid solar arrays would also require to be aligned with the sun, and that would also lock 2 additional degrees of freedom. However, gimbaling the solar arrays and allowing them to perform one-axis rotation frees 1 degree of freedom in the attitude reference determination problem. And these are just 2 of the requirements that normally a spacecraft needs to meet. However, there can be more, such as thermal requirements or the necessity of performing telecommunications. And these other pointing requirements can be stacked on top of the 2 that I described before. Often, the priority that these pointing requirements take are flight mode dependent. So the spacecraft might find itself in a different situation where it might need to prioritize power generation versus telecommunication. So there is not always a clear list of priorities that can be defined univocally for a spacecraft. It can change depending on what the spacecraft is doing throughout the mission. And because the attitude of the spacecraft is a three-dimensional problem, multiple pointing constraints often require compromise solutions tailored to this pointing priority. Also, attitude has to be generated autonomously online. Therefore, we need an easy solution to the optimal attitude reference determination problem. And this is what I'm going to get into in this paper. Now, let's start by defining the pointing requirements that will be addressed in this paper. The first one of which is vector alignment. This can be the case when we have a thruster that needs to be aligned with an inertial pointing request. This pointing requirement can simply be modeled using a dot product where Rn is the direction cosine matrix that maps from the inertial frame to the optimal reference frame. And the dot product between the direction of the thruster in body frame coordinates and the direction of the thruster requested in inertial frame coordinates needs to be equal to 1 to align the thruster. Now, the second requirement is solar array sun incidence. This is the power requirement. We need this requirement to be satisfied in order to generate at all times the power that is required to supply energy to the solar electric thruster. Defining A, the solar array drive axis for the solar arrays, which is body mounted, and S as the direction of the sun in inertial frames. This requirement can be modeled as an inequality where gamma is a parameter that goes from 0 to 90 degrees. Specifically, when gamma is equal to 0, we have our inequality become an equation, and gamma equals to 0 means that we have perfect sun incidence, which means the sunlight is orthogonal to the power generating surface of the solar arrays. And number 3 is we have a soft constraint that can be, for example, a thermal requirement to have a body fixed surface be kept within a certain inertial zone or outside of a certain zone. For example, we might want to keep this thermally sensitive surface away from the sun. This is a softer constraint because it comes from an inequality rather than a strict equality. So after having defined these constraints, let's see how these can be combined together to compute solutions that can satisfy all the requirements simultaneously. And we're going to start by defining the inertial pointing requirement with maximum power generation. Let's start by solving the problem of satisfying the first requirement, which is aligning the thruster with the inertial request. This can be done by breaking the optimal reference frame into 2 rigid body rotations by means of an intermediate frame D. So ultimately, the direction cosine matrix Rn that we want to compute is obtained by multiplying 2 intermediate direction cosine matrices. Now, aligning the thruster is a relatively trivial problem. This can always be solved easily. There are no ambiguities in this. We can simply compute the principal rotation angle and principal rotation vector that characterize the direction cosine matrix Dn that is just a general DCM that aligns the thruster with the inertial request. Like I said, this can always be done, no problem. However, because attitude is a 3-dimensional problem, and this requirement only locks 2 degrees of freedom out of 3, there's an infinite set of solutions that satisfy the first requirement, that is to align the thruster. Therefore, we're asking ourselves the question, how do we find the solution among this infinite family of compliant solutions that also maximizes the power that can be generated by the arrays? Well, because we still have 1 degree of freedom that we haven't enforced, we can exploit the rule about the aligned thrust to compute the solution that is also optimal for the solar arrays. And by defining the thrust direction vector as the principal rotation vector for the second DCM, that is RD, we can leverage an interesting attitude parameterization that is presented by the classic Rodriguez parameters. And we define the classic Rodriguez parameters CRP set Q as a function of T, which is the tangent of C over 2, where C is the principal rotation angle. Now, writing this direction cosine matrix RD as a function of Q, it is possible to impose the orthogonality condition, that is that the solar array drive axis is orthogonal to the sun. And that boils down to this quite elegant equation f of t, which is fairly easy to analyze because it's the ratio between a second order term and another second order term that is never 0. And the coefficients a, b, and c of the numerator are functions of known parameters. These terms come from the knowledge of the thruster direction vector and body frame coordinates, the solar array drive axis, and the location of the sun, which comes from sensor measurements. Now, to find the optimal attitude, we simply need to equate this term f of t to 0 and solve the equation, which is a fairly easy task. We all know how to solve second order equations, and the denominator is always equal to 0. So it is possible to define the discriminant b squared minus 4 times a times c. However, we also want to keep in mind that there's a third constraint that is posed by the keep out zone. So analogously to what has been done for the solar arrays, we can define a function g of t, which basically describes the angle between the thermal sensitive surface and the direction of the sun. The reason why we do this here is that we want to keep in mind which solutions we want to pick in order to maximize both for power generation and also to try and get the best solution that we can for thermal considerations. Therefore, if the delta of our second order equation is higher than zero, higher or equal to zero, I should say, there are two solutions that are equivalent in terms of power generation. They both put the solar array drive axis orthogonal to the sun. Therefore, we can choose whichever solution C1 or C2 also maximizes the function g of t. Now, this is no guarantee that g of t is going to be higher or equal than the cosine of theta. So we have no guarantee that the third constraint is also going to be satisfied. However, we can choose whichever solution gets us the closest. Now, the problem when the delta is negative is that there is no solution that can simultaneously align the thruster with the inertial request and also maximize the power being generated by the arrays. However, it is still possible to differentiate with respect to t and compute the function f prime of t and set that equal to zero to compute the solution for psi that gets us the closest to that orthogonality condition for which power generation is maximum. We have two solutions, psi1 and psi2. However, these are not equivalent. We need, in this case, to pick the one that maximizes the absolute value of f of t to ensure that we are generating the maximum amount of power at all times. And just a quick note on these results. We can define three angles. The first angle, beta, is a function of the geometry of the spacecraft. It is the angle between the solar array drive axis and the thrust direction vector in body frame coordinates. The angle delta is the angle between the sun direction and the inertial thrust request. And gamma is the angle between the solar array drive axis and the sun. So these three angles are, as I was saying, the first one is a function of the geometry of the spacecraft. The second one, delta, is a function of the spacecraft's position along its trajectory. So it's a function of the mission. And gamma is a parameter that defines the performance in terms of power generation of our spacecraft. It is interesting to see how although this problem is four-dimensional because it describes the mutual orientation between four different vectors, it is possible to describe gamma as a function of beta and delta. And this shows us that by picking a favorable geometry for our spacecraft, we can ensure that at all times we can generate the maximum amount of power. That is, when the solar array drive axis and the thrust vector are orthogonal, we are independent of the thrust inertial request and the sun direction, and we can always generate the maximum amount of power. However, when these vectors are not orthogonal, our ability to generate power depends on the geometry of the spacecraft and on the mutual orientation of the sun and the inertial thrust request. Moving on, it is interesting to analyze what happens when there's a lower bound on the power that we need to generate. This means that we might be in a situation where we don't need to generate the maximum amount of power at all times. That is, we can settle for less power than we can generate at that specific location in space. This is while still trying to enforce the constraint that the thruster is aligned with the inertial request. So we take the same steps as before. We can break down the reference generation problem into two consecutive DCMs, and we start by doing the same, where we still compute the dn direction cosine matrix by aligning the thruster with the inertial request. However, the difference here is that when we can relax the assumption of generating the maximum amount of power, we don't have an equation in f of t anymore, but we have f of t bounded by these terms negative k and plus k, where k is equal to the sine of gamma. Therefore, instead of having an equation, we have a system of two inequalities for which the solutions define a range of principal rotation angles for which we are compliant with the power requirements at that state. Therefore, we can define three different parabolas, one of which is just at squared plus bt plus c, and the other two are functions of the same coefficients a, b, and c, plus this term k that defines our relaxed power conditions. Now, we can see that when k goes to 0, all the three parabolas are equivalent. The goal is once again to find the range of values for t such that y plus is higher than 0 and y minus is lower than 0. And obviously, because this is a problem that depends on second order equations, we solve this the only way we know how, which is by defining a bunch of discriminants. Now, what does this mean? These are the solutions for a case in which the delta of the base parabola, b squared minus 4ac, is higher than 0. So for a case where the maximum power requirement case has two solutions. We can see here in the plot on the right, without getting too much into the math, but when the value k is equal to 0.25, we don't have just two solutions. We have two ranges of solutions that encompass the two solutions that we would have found previously. Therefore, as we relax the assumption of maximum power generation, we can find broader ranges of solutions within which we are compliant. And here is the same situation where we further relax this power allowance where k is equal to 0.94. And we can see that these two ranges of values for t keep growing more and more as we make our power requirement less tight. What does this translate into? Here we have two plots on which on the x-axis we can see the principal rotation angle, and on the y-axis we have different values of k. Now the plot on the left shows a case for which delta is higher than 0, where we can see what I was discussing before. So for k equal to 0, so when we enforce the maximum power requirement, we have only two solutions, but as we relax that, these two solutions branch out into two ranges of solutions. The case on the right is the case where we have a negative delta. Therefore, for a certain range of k values, we only find one solution that is a suboptimal power generation because we cannot get the solar array drive axis to be orthogonal to the sun until we cross a critical k value for which our solution starts branching out into a region of compliant solutions. Now, why is this interesting? This is interesting because there might be a range within our compliant solutions that is also compliant with another pointing constraint, such as the thermal constraint, where we have another ranges of solutions that we want to be able to overlap with the power compliant solutions in order to find the principal rotation angles that ensure that all our requirements are being met. Moving on to the solar array reference generation, this is important to discuss because up until this point, we only have discussed the reference generation for the attitude of the spacecraft. Now, we want to discuss the reference generation for the solar arrays, which also rotate, and therefore they need to rotate according to our needs. So in the case where we want to generate the maximum amount of power, the problem is relatively trivial. We can define a vector in the reference frame that is just a function of the solar array drive axis and the location of the sun in the optimal reference frame. Once we compute this, it is easy to compute a reference angle alpha r, which is simply the arc cosine between the nominal orientation for the power generating surface normal and the reference normal. Now, this is when we want to generate the maximum amount of power. However, what does this problem look like when we have upper bounded power generation? Therefore, we don't want to generate too much power. This can be the case when we are flying very close to the sun, such as during flybys with the inner planets, where generating too much power can cause thermal problems such as overheating the spacecraft. Now, it is possible to repeat the same problem as before, where we put a lower bound on the function f of t, This time, this lower bound is given by the parameter k. We can solve the same set of equations. They're having, in this case, two bounds. And in the plot on the right, we can see that our two ranges of solutions become four ranges of solutions. Now, this is solvable, but it makes the math significantly more complicated, unnecessarily so. In fact, there's an easier way to solve this problem. We can avoid recomputing a different attitude that is compliant with upper and lower bounds. We can simply keep in mind that whenever we want to generate less power than what would be technically available, we can always rotate the arrays by an extra amount to make sure that the incoming light doesn't hit the power generating surface of the arrays orthogonally, but at an angle that reduces the amount of power being generated. So we compute the same reference BR for the solar array normal. However, when we compute the reference angle, we can leverage an offset angle epsilon that makes sure that the ultimate angle between the incoming sunlight and the power generating surface of the spacecraft is less than or is compliant with the requirements. So whenever we want to limit the amount of power, there is no need to reorient the spacecraft, generate a new attitude, and slew the spacecraft to attitude. It is a lot easier to simply rotate the arrays to an offset to ensure that we are not overheating the spacecraft. In conclusion, this paper has presented the problem of defining the reference frame for a spacecraft subject to multiple pointing constraints. Such constraints are represented by the bore-site alignment, sun incidence on the rotating solar arrays, and soft keep-in or keep-out pointing constraints. This paper provided a detailed description of the attitude spaces compliant solutions to satisfy most of such requirements simultaneously, or when it's not possible to satisfy them simultaneously, by following an ordered list of priorities. The previous point is expanded to include power-related considerations into the reference attitude formulation. Also, the attitude reference generation problem, thanks to the formulation used in this paper, leverages math that is very elegant and also very simple, therefore making it very easy to implement these solutions online, such that they can be computed by the spacecraft without consuming too much memory. And by computing an optimal solution at all times that simply relies on the knowledge of the spacecraft attitude and the knowledge of the sun vector, which comes from sensor measurements. And that is all. If you have any questions, this is how you can reach out to me. Thank you all very much for listening to this presentation, and I wish you all a nice day.